Hello friends. So in last session we started exercise number 4.2 and let's continue with it. So in that the next question we have is number 8, in which we have given 111 ABC a square b square c square equals to a minus b minus c minus a we have to prove. Now this is one of the most fundamental kind of proof, and if it is possible, so keep this result in your mind, which will help in some of the questions, right? So let's take the LHS. So in LHS we have 111 ABC a square b square and c square. Now I'll tell you 2 points that always go with the property when we get at least 2 zeros in the determinant. At least 2. If you get more than 2, then it's okay, but at least try to get 2 zeros, and once we get 2 zeros, then apply the expansion. Okay. And second point, that when we want zeros in the row, we have to apply column operation, and we want zeros in the column, we have to apply row operation. That means, just check, we have 1 1 and 1. That means we can get 0 in first column. So to get zeros in first column, we have to apply the row operation. So the row operation can be R2 to R2 minus R1 and R3 to R3 minus R1. So by using this operation, we will get 1 0 0 a b minus a c minus a square b square minus a square, c square minus a square. Now I can give simplification in the determinant only that b square minus a square can be b minus a b plus a, and here it is c minus a c plus a. Now we can take something common from the determinant, so we have to divide with b minus a in the second row and c minus a in the third row, right? So let's go with the operation. So the operations are R2 will be divided by b minus a and R3 will be divided by c minus a. So if we divide with something, we have to multiply with something also. So now we have 1 0 0 a 1 1 and a square b plus a c plus a. So now as we discussed that before expansion we have to get at least 2 zeros. Just check, we have 2 zeros. So after this step, if you give the expansion, then it's also okay. But if you don't want to give the expansion, so try to get another 0. So just check, it's 1 1. So we'll get 0 in the column. So we'll get R3 to R3 minus R2. So by using this, we'll get b minus a, c minus a in the determinant. It's 1 0 0 a 1 0 a square b plus a, and it's c minus b. Now if you just check, this will become your upper triangular determinant. Upper triangular determinant means what? That just check the principal diagonal elements, and all the elements below principal diagonal elements are 0. All the elements below principal diagonal elements are 0. So this type of determinant is known as upper triangular determinant. And in this case, the answer of determinant is directly equals to the multiplication of the principal diagonal elements. So in this case, the direct answer will be 1 into 1 into c minus b. And now as we can take minus common from first term and this last term, we'll get a minus b, b minus c, c minus a, which is what we want to prove in the RHS. Okay, so hope you understand this. It's one of the fundamental question. So 2-3 points we discussed that you need to keep in your mind. Okay, in next question we have number 9. We have 1a cube, 1b cube, 1c cube equals, to prove a minus b, b minus c minus a into a plus b plus c. Okay, so let's go with the LHS in this. So we have 1a cube, 1b cube, 1cc cube. So let's follow the same rule which we already discussed, that if we need 0 in the row, we have to apply the column operation. So in that, we'll apply C2 to C2 minus C1 and C3 to C3 minus C1. So by using this property, we'll get 1a cube 0, b minus a, b cube minus a cube 0, c minus a, c cube minus a cube. Now let's give simplification inside determinant only. So this will become b minus a into b square plus ab plus a square, and in third column it's 0, c minus a, c minus a into c square plus ac plus a square. Okay. Now we have b minus a common in the second column and c minus a common in the third column. So let us divide with it. So C2 will be divided with b minus a and C3 will be divided with c minus a. So if we apply these operations, so we have to multiply with b minus a into c minus a. So it is 1a cube 0 1 b square plus ab plus a square and 0 1 c square plus ac plus a square. Now again you can directly expand this determinant, or we can get further 0 also, right? So for that, let's go with this second column. So now C3 will become C3 minus C2. So b minus a, c minus a, 1a cube as it is, 0 1 b square plus ab plus a square as it is, it's 0 0. Now just x square minus b square, ac minus ab, and a square minus a square will be cancelled. So it's again a form of lower triangular determinant. It's a lower triangular determinant because just check that the principal diagonal elements and above that all the elements are 0. So it's a form of lower triangular determinant which has again answer equals to the multiplication of principal diagonal elements, right? So from that we can say b minus a, c minus a, 1 into 1 into c square minus b square plus ac minus ab. So we have b minus a, c minus a. Now from these two terms I can do the factorization, c minus a into c plus b, and from these two terms I can take ca common, so it will be c minus b. So now it's b minus a, c minus a. From these two terms we can take c minus b common, and inside the bracket we'll have a plus b plus c. So the final answer will be a minus b, b minus c, c minus a into a plus b plus c equals to RHS. Okay, so hope you are clear with it, right? Just follow simple fundamental rules, right? So this will become very easy for you. Let's talk about next question. In it, okay, then in number 9, it was the second part of number 8, now it's number 9. In number 9 we have x, y, z, x square, y square, z square, and y, z, z x, and x, y equals to, we have to prove x minus y, y minus z, z minus x into x y plus y z plus z x. This we have to prove. Okay. So very first thing, just observe, we have x, x square, y square, z, z square. So we'll try to get x, y and z in this column also. So what we'll do first, let us multiply, let us first of all write down the LHS. So in that it's x, y, z, x square, z square, y, z, z x and x, y. Now, the very first thing, if you don't want to go with the 0, so just go with the operation R2 to R2 minus R1 and R3 to R3 minus Y1. The reason is, if I apply this operation, then I will get x, y minus x, z minus x, x square, y square minus x square, z square minus x square, and here yz, it's zx minus yz, and it's xy minus yz. Now by using this, you just give expansion in the determinant only. So this will become y minus x into y plus x. This will become z minus x into z plus x. Now in third column we have yz. Now just check, if I take minus z common, so I will get y minus x, and if I take minus y common, then I will get z minus x. Now as you observe that in the second row we have y minus x common, and in the third row we have z minus x common. So what we'll do, we'll divide with y minus x in second row, and we'll divide with z minus x in the third row. So by using this, we can multiply with y minus x into z minus x. It's x 1 1, it's x square y plus x, z plus x, and here it is yz minus z minus y. Hope you all understand this point. Now go with the 0. So just check, we have 1 1, so we'll get 0 over here. So for that we have to apply the row operation, that is R3 to R3 minus R2, which is y minus x, z minus x, x 1 0, x square, y plus x. Now just check, if we multiply this with minus and adding to the third row, we'll get xx cancel. So we have z minus y with yz minus z, and again it is z minus y. Okay, now let us divide with z minus y in third row. So R3 will be divided by z minus y, so we have to multiply it with also. So it is x 1 0, x square y plus x 1, yz minus z1. So what we get? So now either go with the expansion or go with the 0 again. Okay, so what we'll do, let us do operation between these two columns to get 0 over here. So now it is C2 will become C2 minus C3. So it is y minus x, z minus x, z minus y. It's x 1 0 remain as it is. It's x square minus yz. It's y plus x plus z. Here 0, and it is yz minus z and 1. Okay, and now if we expand from the third row, because it's not a kind of upper triangular or lower triangular, right? Because this element is not 0, so we cannot go with the upper triangular. So we have to expand from the third row, and by expanding from the third row, we'll get y minus x, z minus x, z minus y as it is, y minus x, z minus x, and z minus y as it is, into, from the third row it is 1 into x1, x square minus yz, and y plus x plus z. Okay, so now as we give the multiplication, so y minus x, z minus x, z minus y into multiplication, it's xy plus x square plus xz minus x square plus yz. So just check, we can cancel out x square and x square, right? And now from these two terms, these three terms, if we take minus common, so x minus y, y minus z, z minus x into xy plus yz plus zx, which is equals to RHS. Hope you all understand this one. Okay, next question. So in next question we have number 10. In that first one we have given x plus 4 2x 2x, then 2x x plus 4 2x, and 2x 2x x plus 4, which is equals to, we have to prove 5x plus 4 and x minus 4 whole square. This is what we have to prove. Okay, now I'll tell you a rule. When you observe a determinant in form of a symmetric form, just keep a point in your mind. When we observe the determinant in form of symmetric, right, symmetric form, so always go with the operation where to use any two rows or two columns and add in the third one. One second, when we have a symmetric form, just check, it's a symmetric form of determinant. You can just check all rows and all columns, you find that it's a symmetric form. So when we have a symmetric form of determinant, always follow the rule where we can use any two row or any two column and add in the third one. Now you can use any two rows, eh? Either I can go with first and second and I will add in the third one, or I can go with first and third and I will add in the second one. The same thing you can apply in the column also. So right now what I will do, I will go with the R2, R12, R1 plus R2 plus R3. So after applying this, the determinant I will get as 2x plus 2x plus x, that is 5x plus 4. Similarly 2x plus x plus 2x, that is 5x plus 4, and here also it is 5x plus 4. So 2x 2x, x plus 4 2x, 2x, x plus 4. Okay. Now if you follow the column operation, then this thing you can get in the first column, right? Now we just check, we get 5x plus 4, 5x plus 4, 5x plus 4 in the first row. So I will do the operation where R1 will be divided with 5x plus 4. So I have to multiply it with also. So now I'll get 1 2x 2x, 1 x plus 4 2x, and 1 2x x plus 4. And now it's one of the simplest form here. Now that go with the zeros, right? So in that we'll go with C2 to C2 minus C1 and C3 to C3 minus C1. So we'll give 5x plus 4 as it is. It's 1 2x 2x as it is 0. Now just check, x plus 4 minus 2x, that is 4 minus x, 2x minus 2x 0. Here 0 0 and 4 minus x. By using this we just get lower triangular determinant. So answer will be 4 minus x into 4 minus x into 1. So hence your final answer will be 5x plus 4 into 4 minus x whole square equals to RHS. You always get such kind of form and such kind of easiness when we have a symmetric form of determinant. Just check number 2 in that. In this number 2 we have also, we have y plus k, y plus ky, and y plus k, and you have to prove its k square as 3y plus k. Now just observe, it's again a form of symmetric form of determinant. So just follow the same operation. I'll give you a minute so to check that whether you go with the row operation or you can go with the column operation, we'll get definitely something common in either row or column correspondingly what operation you apply. Okay. So just check. In this case, let us go with the column operation. So if I multiply second and third column, and if I add in the first one, that means in this case if I apply with the C1 to C1 plus C2 plus C3, what will get? We'll get y plus k plus y plus y, that is 3y plus k. Similarly y plus y, 3y plus k, and here again 3y plus k. So it is y plus ky, and y plus k. Now if you just observe, I put all both the sums together. So here we applied row operation, therefore we can get common in the first row because we added both the rows in the first one. Whereas in this case we applied the column operation and we applied second and third column in the first one, so we get common in the first column. So according to the operation you apply, you will get something common in that respective row or column where you add remaining two rows or columns, right? So now what we'll do? We'll divide with 3y plus k in the first column. So we have to multiply it with also. So we'll get 1, 1, 1, y plus k y plus k. And now to get 0, it will be r2 to r2 minus r1 and r3 to r3 minus r1. So it is 3y plus k 1 0 0 y k 0 and y 0 k. So it's again a form of upper triangular determinant. So answer will be 1 into k, that is k square into 3y plus k, which is what we need in the RHS. Okay, so you have both the cases together. In first I applied the row operation and in second I applied the column operation. You just check the corresponding patterns are same in both the cases. Okay, so hope you understand this. In next question, number 11. In that we have first, we have a minus b minus c. It is 2b to c. Then 2a b minus c minus a to c. 2a 2b c minus a minus b equals to, we have to prove a plus b plus c whole cube. Now in the previous question we discussed that if we have a symmetric form of determinant, go with any 2 row or 2 column and add in the respective third one, right? Now just in this kind of cases, I'll give you another rule. When we have a similar type of elements in principal diagonal elements and remaining elements are similar with each other. In this case, similarity means what? Just check. There are 3 terms in principal diagonal elements, whereas in remaining elements there is only single term. Okay, so in this type of cases also you can go with the operation which we discussed in the previous one, that go with any 2 row or 2 column and add in the third one. But these are the particular cases. You cannot go with both the conditions. Any one of the conditions will helpful to you. That means either row operation will helpful or the column operation, not both. Okay, so just check. If I go with the column operation, so if I add second, third and second column in the first one, I will not get this term. Just check. What if I get multiply third and second column and add in the first one? I will get 2a plus a, that is 5a. 2b plus b plus b 2b, that is 5b, and 2c plus d, that is 5c. Whereas if the same thing I go with the row operation, just check. If I multiply second and third row with 1 and if I add in the first one, I will get minus 2b plus minus b plus 2b, that is b, minus c plus 2c, that is c, then minus a plus 2a, minus c plus 2c, that is c, 2a minus a, that is a, and 2b minus b, that is b. Right? So in this case the row operation will helpful to us. So let's go with it, that r1 to r1 plus r2 plus r3. So it will be a plus b plus c, here a plus b plus c, and here also a plus b plus c. Remaining rows are same. Now let's divide with a plus b plus c in the first row. So as we divide, we have to multiply also. So 1 2b 2c, 1b minus c minus a 2c, and 1 2b c minus a minus b. Now it's very similar, familiar to all of you, that once we get 1 1 1, what we'll do? We'll do c2 to c2 minus c1 and c3 to c3 minus c1. So we'll get a plus b plus c, 1 2b 2c, 0. Now just check, b minus c minus a minus 2b, so we'll get minus a minus b minus c. Similarly 2c minus 2c 0, here 0 0, and we'll get minus c minus a minus b. So now it's in form of lower triangular determinant. So multiplication will be principal diagonal elements. So it will be a plus b plus c with 1 into minus a minus b minus c into minus a minus b minus c. So we'll get a plus b plus c whole cube, which is equals to RHS we observed. Clear everyone? Right? You just observe the pattern and it will become very easy for you to expand. Okay? Similarly, we have second number in it. So in second number we have x plus y plus 2z with zx, zz, then x, y plus z plus 2x and x, and it's y by x plus z plus 2y, and the proof we want is 2 times x plus y plus z whole cube. Now just observe again a similar kind of form in this we discussed. Now but the thing is, here we applied row operation, but here row operation will not work for us. Just check, if we go with the row operation, then we'll get z plus 2z, which is 4z, x plus 2x, and y plus 2y. So as this compared to this, here row operation will not follow us. So which will helpful to us? In this case, the column operation. So just to go with that, that c1 will become c1 plus c2 plus c3. So now it will become x plus y plus 2z, then it will become 2 times x plus y plus z. Similarly, y plus z plus y plus z plus 2x. So it is 2 times x plus y plus z. And similarly, in the last third element, z plus x plus z plus 2y, that is 2 times x plus y plus z. So it is x, y plus z plus 2x and x, y by x plus z plus 2y. So now we can divide with c1 to 2 times x plus y plus z c1. So we have to multiply with also. So we get 1 x, y plus z plus 2x x, y by x plus z plus 2y. Now the zeros to get, that is r2 to r2 minus r1 and r3 to r3 minus r1. So it is 2 times x plus y plus z with 1 0 0, it's x. As we did multiply this with minus and adding the second one, so y plus z plus 2x minus x, that is x plus y plus z, x minus x 0, y 0, x plus y plus z. And now again it's a form of upper triangular determinant, right? So the multiplication of principal diagonal elements will give us 2 times x plus y plus z into 1 dot x plus y plus z dot x plus y plus z, that is x plus y plus z whole square. Hence your final answer will be 2 times x plus y plus z whole cube, which is equals to RHS. Right? So hope you understand this, that always follow the pattern. Try to keep the points that I told you, that if we have a form of determinant, so follow that property. It will be very easy to solve this expansion. Okay?